Alright, grade 10s. So to start off our session this evening, what we're going to do is we're going to go through balancing some equations. Okay, balancing some equations. Okay, so when it comes to balancing an equation, okay, a balanced chemical equation, now the theory behind it is that it represents chemical change and shows the law of the conservation of matter in action. Okay, each side of a balanced chemical equation must have the same number of each atom. Okay, the amount of reactants must equal the same amount of products. Okay, it demonstrates or shows the correct ratio in which the substances react and form. Okay, in other words, even if macroscopic amounts, large amounts of reactants form macroscopic amounts of products, we know the ratio of reactions to products because of the balanced equations. Okay, so let's take a look at a unbalanced equation first. Okay, let's take this unbalanced equation. Okay, somebody explain to me what's going on. So read the whole equation from left to right. Reactants and products. What's reacting with what and forming what? We all should be able to do this. Anyone? Now.
Nitrogen is reacting with hydrogen.
Mm-hmm.
I don't know what it forms. I forget the name.
Thanks for your honesty, Jordan. Okay, but you are right about the reactants. Nitrogen is reacting with hydrogen. Okay, a simpler way to read it: N2 plus H2 gives us NH3. Okay, cool. So one of the questions could be, yes, to give the name of the product, the chemical name. Yes, the name. Okay.
What's the G? What's the thing in brackets?
Good.
Does that count?
Excellent question. Thanks, Mia. Thank you. Because if you didn't ask it, I probably would have explained it anyway. But thanks, I will explain it now. Excellent question. What is the G in brackets? Remember, we've learned states of matter previously. Yes? Am I correct?
Yeah.
Yes, we have. Okay, and the states of matter that exist are solid, liquid, and
Gas.
So what does the G stand for?
Gas.
There we go. Perfect. All right. So the G in brackets over there tells us the state of the reactants and products. So it's actually nitrogen gas is reacting with hydrogen gas, and it's forming ammonia gas. NH3 is ammonia. N-I-A. With that being said, the equation is unbalanced. Okay? On the left, all right? Okay? We see that the left side of the equation has 2 nitrogen atoms. Why? It's N2. Not like the freeway. Okay, but N2. And also, we have 2 hydrogen atoms on the left as well. Let's go to the right-hand side. On the right-hand side, I only have 1 nitrogen atom bonded to 3 hydrogen atoms, or 3 hydrogen atoms bonded to 1 nitrogen atom. So that means my left is not equaling my right, and my right is not equaling my left, and this is not that, and that is not this. Sorry if I crescendoed there at the end. Sorry. So that means we've got to go and do something about it. Okay. We use what's called balancing numbers. All right? Balancing numbers. By balancing these equations, what we're going to do, we're going to show that the mass of the reactants equal to the mass of the products, or the number of atoms on the left are going to equal to the number of atoms on the right hand side. So basically what I need to do is I need to go ahead and basically I'm going to use another color for this. If I need to make sure I got the same number of nitrogens over here, I need to put a 2 in front of NH3. Okay, I need to put a 2 in front of NH3. Okay, this means now that I've balanced my nitrogen, so I can have a little checklist here of my element. Nitrogen is now balanced. Okay, my hydrogens, I have 3 on the right and 2 on the left. But remember, think of this 2 as doubling everything here. Before I had 1 nitrogen atom, okay, with 3 hydrogen atoms bonded to it. Now I've got 2 ammonia atoms, or 2 ammonia compounds now. Alright, 2 ammonia compounds. Think of it like that. So I have double the amount of nitrogen and double the amount of hydrogen. So what's 3 times 2? This is not a rhetorical question. Someone answer it, please.
6.
Thank you, Jordan. Yes, 6. So that means I have 6 hydrogens on my right and only 2 on my left. What balancing number needs to go in front of H2 in order for me to also have 6 hydrogens on the left?
A 3.
If you say 3, you're correct. Alright? 3 times 2 is 6. So my hydrogens now, in fact, are balanced. Alright? My hydrogens now, in fact, are balanced. Alright? So, that makes perfect sense. I'm happy with that. I've balanced now my equation. Let's take a more difficult equation. Let's take, and I'll do this in white. What's the name of this atom or element on the periodic table? Anybody?
Iron.
Iron. Okay. Plus O2, we all know that's oxygen, gives us Fe2O3. Okay. So question earlier was, naming compounds, naming them, actually giving them the name. Okay, well, this is also iron oxide. All right, it's also iron oxide. Okay, usually a better name would be iron trioxide because there's 3 oxygens. All right, but the name is still given it as iron oxide. Okay. When we get to compounds or molecules such as CO2, what do we know this as?
Carbon dioxide.
Carbon dioxide. Why do we call it carbon dioxide? It's still got oxide in it. We're very familiar, but why does it have di?
Because there's 2 oxygen atoms.
Because it's 2 oxygen atoms. Okay, so when we're naming certain compounds, we're looking at how much also of a substance do we have. Alright, so we can give the proper chemical name. Okay, the exception, if Fe2O3 is still iron oxide. Okay, with a little bit of an exception. And in fact, I'll even fact check that quickly. In one of my other resource booklets. I'll fact check it quickly. Yes, fact check correct. Iron oxide.
JB?
Yes.
If you say ferrous oxide, is that wrong?
So let's see if we can balance this equation, girls. So like I said, this iron 3 here, that just means it made 3 bonds. Okay, so we obviously know that we have one iron here. That's just the amount of bonds that it made. Doesn't mean I have 3 of them. Okay, so I have one iron, 2 irons, and I have 2 oxygens, and I have 3 oxygens. So I'm definitely got what may look like to every scholar as a mess. Alright, I have a mess. Okay, so what I want to do is I want to clean this mess up. Okay, so how do you think we're going to go about balancing this equation? Can anybody want to take a stab? What's the best way to approach this one?
2, which made iron 4 and oxygen 6. So then I times iron on the left side by 4 and oxygen by 3 on the left side.
Excellent. 100% correct. Excellent. Thank you, Famke. Okay, I'll repeat that. So, obviously, the approach that Famke had was, let's write out everything we have on the left and everything we have on the right, and let's compare or see that way. For me, it's easier to see because I've been doing this for 8 years. Okay, so I can see, okay, immediately what's unbalanced. Okay, so simply putting a 2 or doubling up our products. Remember, we must understand that the left side is reactants, 2 things reacting with each other, and on the right hand side is our products, what has formed after the reacting has happened. So if we double everything on the products, that means we've made now, instead of 2 iron we have 4 irons, and instead of 3 oxygens we have 6 oxygens. So that makes it easy now to go and balance our reactants. 2 times 2 for iron is 4, and put a 4 in front of iron, and then on oxygen 3 times 2 is 6, so we put a 3 in front of oxygen. 3 times 2 is 6, so we have iron all balanced and we have oxygen all balanced. Okay, I'm just writing down the element name here as on the periodic table and just balancing it out. Okay, so shall we practice a few examples of these maybe? Alright, so what we have here, we have 5 chemical equations all unbalanced, and what I require you to do is balance these equations. These are quite simple, okay, and we will progress into a bit more complex ones. Okay, we'll also progress into word equations where we actually have to write down the chemical equations for the word equations, but that's a bit later on. Okay, so let's try these, see how well we do. Okay, so we have the first one done for us. Okay, we have balanced Na plus O2 gives us Na2O, which is sodium, plus oxygen gives us sodium oxide. Okay, so what we did was we put a 2 in front of Na2, and this was by balancing oxygen first, because we noticed on the left we had 2 oxygens, and on the right we only had 1. Okay, so we wanted to make sure we take care of oxygen first. So that was the easiest atom or element to balance. Okay, we've taken care of that, and then we can go ahead and take care of our sodiums. Okay, cool. Which we put a 4 in front, because on the right we have 2 times 2 sodium, so we have double the sodiums here, which is 4. So we put a 4 in front of sodium on the left, and now we have a balanced chemical equation, and we're all happy. Right. I nominate someone to do the second one. B. Jordan. Balance B for me, please. We have iron plus oxygen gives us iron oxide.
I don't know if I did it right, but I put a 2 in front of the oxygen. Behind the arrow, like on the right side.
On the right hand.
Yeah.
Okay, cool. So yeah.
No, in front of the oxygen.
Okay, so you had the right concept. Okay, cool. So let me just fix the teaching there. So the 2 that you see where I placed the 2 in front of FeO, that 2 is for the entire compounds. That means every atom in that compound is doubled, including your oxygens. Okay? So unfortunately, you cannot just balance one thing on the product side. You need to put the balancing number in front of the whole compound or molecule. Okay, Jordan, does that make sense?
Yes.
Okay, cool. So you had the right concept. So just make that correction. So if you did that, that means your oxygens are balanced. So now if you can see if you can fix this now, what else needs to be balanced here? So don't focus on your answer, just focus on the screen here. What else needs to be balanced? I've got two oxygens, and here I have 2 ions and 1 ion. What do I need to do?
Put a 2 in front of the iron.
All right, there we go. And now we have a balanced equation. So now I have 2 ions on left and right. And on left and right, I have 2 oxygens. So that equation is balanced. C. Mia, I nominate you. Balance aluminium plus oxygen gives us aluminium oxide.
Okay, so on the left hand side, you put a 4 in front of aluminium and then a 3 in front of the oxygen. And on the right hand side, you put a 2 in front of the aluminium.
Okay, excellent. All right, fantastic. That is 100% correct. Okay, talk me through it, Mia, first. Did you balance the right-hand side first and then the left, or the left and then the right?
Oh, wait, okay, I have to remember this now. I think I did the right hand side. No, wait. Yeah, I did the right hand side first.
Okay, excellent. I'm going to stop you right there. You know why? Because that's 100% correct. Okay, let's learn from this, people. Okay, on the right-hand side, we obviously got more of both atoms on the left. So we started out with 1 aluminium on the left and 2 oxygens on the left, right? 1 aluminium plus 2 oxygens. On the right-hand side, we end up with double aluminium, so 2 aluminium and 3 oxygen. So wouldn't it have made sense for us to start balancing from the left and then go to the right? Because we probably would have been still sitting with that question and still trying to figure it out. Made sense to rather double everything here on the right-hand side. Okay? And then from there, work backwards from right to left. Okay? So if we double everything on the right, so we have double everything, so 2 times 2 and 2 times 3. So 2 times 2 aluminium, which is 4. Great, I can put a 4. Makes simple because I only had 1 here to begin with. Alright, so that's simple. And 3 times 2 or 2 times 3 is 6 on the right, so 3 times 2 is 6 on the left. Everything is 100% balanced. Okay. I'm going to get involved on the last 2 quickly, especially for this last one here for E, which is hydrogen. This is hydrogen peroxide, by the way. Quite deadly. Okay. So for D was quite simple. We had 1 lithium atom reacting with 2 chlorine atoms just to give us lithium chloride. Okay. So I need to balance my chlorines first. So I put a 2 on the front of the compound lithium chloride, meaning I've balanced down my chlorines. But now I've doubled my lithiums. So I need to go put a 2 in front of lithium on the left. So I have 2 lithium, 2 chlorine, 2 chlorine. Okay. Now hydrogen peroxide. Okay. Which is actually formed by adding oxygen to water. Alright? Who would have figured that? Okay? But when you see a reaction like this, for the first 4, we had reactants forming products. But for E, our product has become our reactant. And what would have been our reactants has become our products. So this type of reaction is called a decomposition. Decomposition reaction. In other words, we are decomposing a product to go back to the reactants. Okay? Breaking something up into its smaller bits. Alright? That makes sense to everybody, yes?
Yes.
Fantastic. Okay. So we're breaking up hydrogen peroxide because we want water and oxygen to separate. Okay? Maybe we want to get water. Or maybe we want to get oxygen. Okay? Doesn't really matter. Okay, but we've broken it up, we've decomposed it. That being said, on the left hand side, we have H2O2. On the right hand side, we have H2O, H2O plus O2. But what I can see that my hydrogens are already balanced already. I have 2 hydrogens on the left, and 2 on the right. But I have 2 oxygens on the left and 3 oxygens on the right. 1 oxygen is from H2O and 1 is from O2. Okay, nothing to panic about. Okay, what would make sense to do is probably double hydrogen peroxide. So if I double hydrogen peroxide, okay, I've now created more of it. So I have now, in total, my elements now, or atoms, I have 4 hydrogen atoms. Initially I only had 2. And 4 oxygen atoms. Initially I only had 2. So now my hydrogens are now unbalanced. So I need to go balance them again. So I throw in a 2 in front of the H2O. Now I've got 4 hydrogens, my hydrogens are done. Now I'll go count my oxygens. My oxygens stand on the left hand side, 2 times 2, so I have 4 oxygens there as well. On the right hand side, well, 2 times 1 here, so 2 times 1 is 2, plus another 2 is, well, 4. Then therefore, according to that calculations, my equation is now balanced. Do we understand? Do we grasp that last one? Any questions on the last one, hydrogen peroxide? Mia, your mic went on and I didn't hear what you said.
Oh, did I put it on?
Yeah.
Sorry.
No, it's okay. No questions from you then, though.
No.
Okay, cool. But we all get that? Maybe just a yes to give me a bit of a peace of mind?
Yes.
Okay, cool. Alright, fantastic. I'm glad we're all getting it. Okay, so what we're going to do now, we're going to slight transition. Okay, I see we're all comfortable with, or more comfortable with writing or balancing equations when they are in their chemical form, like here. Okay. What happens when we get given a word equation? Will we get given the chemical names, right, for these compounds? All right, we get given the chemical names, and now we need to give the chemical formula for them. For example, we'll pick one as a little showboat example before we actually get into practicing them by ourselves. And then we may still have time for Lewis structure. We won't do a lot of word equations because words take a bit longer to write. So let's try this one. Let's pick a simple one. Let's pick potassium, which is a common element found in bananas. Potassium oxide plus water. Potassium's quite healthy, but too much of anything is bad. Gives us potassium hydroxide. Okay, now those words, big words, may throw us off. Okay, it may throw us off. Okay, but we don't panic. Okay, we don't panic. Okay, we cool. Cool. So, first thing we need to find out is look at our periodic table, which should be given to us in our tests and should be given to us in the exam. Okay, let's put it up. Let's have a look. Okay. What is the periodic table symbol for potassium? It's K. So we can write it in brackets on the question paper. It's K. Oxide, we know that involves oxygen. Okay, usually oxide, okay, it's just one O. Water, we know that's H2O. Okay, and potassium hydroxide, well, we know hydroxide is OH, and we know potassium is also K. So we've identified the symbols. We are halfway there. Now we just need to obviously determine how it's written. Okay, so therefore, the equation, chemical equation, will look something like this. K2O plus H2O gives us K, that's capital K, just write that out again, OH. Okay, that is the chemical equation. Okay, now of course we need to balance it as well. So if I have a look, I have 2 potassiums on the left, 1 on the right. I have 2 oxygens on the left, sorry. I have 1 on the left, and I've got 2 hydrogens on the left and 1 on the right. So it looks like I have 1 of everything here, which is very simple. If I double it up like this, let's check. 2 potassium, 2 potassium, 2 oxygen, 1, 2 oxygen, 2 hydrogen, 2 hydrogen, equation balanced. I'm happy. Okay, so because this is a word example, I'll give one more and then we'll call it. Or we'll call it on this one and then I'll explain some Lewis structure. Okay, so I have nitrogen monoxide. Okay, and I'm adding another oxygen to it, and it gives me nitrogen dioxide. Please write out the chemical equation as well as balance it for me. Thank you. Okay, let's have a look at the solution for this one. Okay, so nitrogen monoxide. Okay, obviously know the symbol for nitrogen, and for monoxide, mono 1, so NO. Plus oxygen, we know is O2. Nitrogen dioxide, we all know that one, NO2. Okay, first half of the question all done. Okay, the next part is now balancing. Okay, first thing I notice is wrong is that I got 2 oxygens on the right and 3 on the left. It means I'm going to probably have to double up my right hand side. So if I double up my right hand side, now I've got 4 oxygens and 2 nitrogens, and on the left I only had 1. So I add a 2 in front of the nitrogen in nitrogen monoxide. Now I have 2 nitrogens, 2 oxygens here, plus another 2 gives me 4, which balances out my right hand side because 2 times 2 is 4. My equation is balanced and I'm happy. So with a balancing equation, the trick is just to make sure that you have counted each of your elements and your atoms in your chemical equation and make sure you have the same number of each. If you fail to count, you will fail to balance. Right? It's that simple. Right? I cannot what's the word I'm looking for? I cannot make it more plain or simple or simpler than that. Okay. Practicing these word equations are very helpful, especially for naming the chemical names and recognizing the chemical names and putting them into chemical formula. Okay, which probably might be for your test or exam coming up on Thursday, Mia and Jordan. Okay, just let me know if you need me to do another example. So Lewis structure is revision, or should be. When I say should be, I mean like it should have been taught last year. Lewis structure is basically demonstrating how 2 atoms are forming. In other words, how they come together, and actually showing visibly the bonding and how they're actually bonded to each other. Okay, and Lewis diagrams. Okay, what do they represent? they represent the valency, okay, of an atom. So the atom's valence electrons, okay? To remind ourselves, the valency of an element is the number of electrons an atom of the element can donate, gain, or share to form a bond. Okay, it's because of this bond sharing, okay, that we have reactions, or because of the bond sharing that we can react and form a totally new product by reacting two different atoms together, okay, or two different elements. Okay, so with Lewis structure, okay, we make use of X's and oversized periods or dots. Okay, we use this to show how a bond has formed. Let's take a look at an example. Let's take a element that cannot exist by itself. Let's take Cl2. Okay, which you all know is chlorine. So if I have Cl, I go look at my periodic table, where the heck in which group it is. It's in old group 7, new group 17. Okay, old group 7. Okay, meaning that it has 7 electrons, or core electrons. Okay, and basically, okay, we just draw 7 electrons around it. So we start by 1, 2, 3, 4, 5, 6, 7. Now remember, on the periodic table, the groups and the way the valence electrons works, it starts by going 1, 2, 3, 4, and then 3, 2, 1. The reason why it starts 3, 2, 1, and chlorine is in group 7, which is the group of halogens, and it's when it goes 3, 2, 1, chlorine is in that group of 1, because it's only got 1 electron to share. In other words, only this electron is available to be shared with another atom or another element, whether it's of its kind or of a completely different or separate element or atom. Okay? Because these that we see here are pairs, electron pairs. Okay? They are known as lone pairs. Remember, 2 is a pair. Okay, they always say 2 is a couple, 3 is a crowd. Okay, well, if you have a pair of shoes, you have 2. Right? 2 pairs of shoes, you'd have 4. Remember, you have 2 feet. So you have 1 foot and another foot gives you feet, 2 feet. So you have a pair. Okay? Same thing. Just making sure we all understand what the word pair means. Okay, P, not the fruit, of course, but P-A-I-R. Cool. So chlorine only has 1 electron or valence electrons that it can use or can be made available to bond with another atom or element. So let's take Cl, and I'm going to use X's now. Okay. And I'm going to write the lone electron on this side to show that these two are going to share. Okay, they're going to share an electron. They're going to share. They're going to form a bond. How will we write that out for Lewis structure? Simple. Cl. Okay. These two are going to come in line with each other. So that is the bond from this chlorine, and this is the bond from the other chlorine. This is one arm, one bond. I have shown the sharing of 2 electrons being shared. If they're being shared, they form a bond. And I simply add in the lone pairs of both chlorine atoms as well. I still need to show the lone pairs, but this here, this is the bonding pair. In other words, the 1 valence electron from either chlorine came together, and I've shown them by writing them in bond form in Lewis structure. Okay, so we used a example of when the same element was bonded to itself. But what happens if we want to draw a Lewis structure for a compound? Let's take a compound, for example 2, as NH3. Okay, we have NH3. Okay, so we obviously all know that with Lewis structure, a single dot will represent an unpaired electron, and a double bond would obviously represent paired. Okay, so the point of us using Lewis diagrams is to show how two or more atoms are bonded together. That's all. Okay, so only when you're doing Lewis structure, only the valence electrons are involved. They're only involved. Okay, in the chemical bonding. The core electrons, they are held too tightly to the nucleus, so they can't get involved. That's why you draw lone pairs, because those lone pairs of electrons, they are just too close to the nucleus. Right? They're not in the valence, in the outer shell. Okay, that's all. Okay, we can also use Lewis structures to show the bonding of electrons of a compound, which I'm about to do right now. So we know nitrogen is in group 5. Okay, so it has 3 valence electrons. Okay, in other words, the Lewis structure diagram for nitrogen is just like this: 2, 3, 4, 5. It has 1 lone pair, but it has 3 valence electrons. In other words, 3 lone electrons waiting to be shared. Okay, and hydrogen only has 1 valence electron. Okay, it's probably the most simplest or straightforward atom that exists, or element that exists in the periodic table. So nitrogen actually has space for 3 hydrogens, as you can see. Okay, only 3 and not 4. All right, not even 6 or even 5. Only has space for 3. Okay, so what we're going to do is we now need to say that nitrogen has space for 3 hydrogens to bond to it. Okay, 3 of them. So if you want to draw the Lewis structure for this, let's come over here. We have nitrogen with its lone pair up top here, and its 3 valence electrons. And all we do is when we bond in the hydrogen, we draw in the X's, and we write the hydrogen here on either side. So this indicates the bond between hydrogen and nitrogen, and so do these other 2 as well. Okay, that they have bonded to each other. Okay, that's the point. Okay, it's to show the bonding of electrons together. Okay, and that's basic. That's basically what it is. Okay, Lewis diagrams. Any questions on this one? And that concludes my presentation on Lewis structure as well as balancing chemical equations. Please stay tuned for our next video where we'll have a look at our next topic.